Prakash. Today I am explaining about finite state fields in subject state switching theory, logical designing. So here I am today explaining about the state missions topic. So let's begin. So finite state missions, understanding the basic and applications. Uh, explore the fundamental concepts and derive uses of finite state machines a powerful tool in the conception of conception and system designing. And what is a finite state machine? Means a finite state machine FSM is a mathematical model of a conception that possesses a limited and a defined number of states. Discrete state and FMS means finite state machines operate within a finite set of distinct states. Input drives transition. States change dynamically based on specific inputs. Sequential behavior of a finite state machine, ideal for modeling and existing theoretical logic, step logic. Next, core concepts of a finite state machines. Every finite state machine is built upon several fundamental elements that discrete its behavior and functionality. Finite state machines, a defined collection of possible states, including an initial start state, and a transitional function. Rules that specify the next state based on the current state and input. Trigger inputs. Every event or data that causes the final state machine to move from one state to another state. And optional inputs. It's an actions or rules generator generator when entering a state or the next types of SMS, FMS means types of finite situations, dis- deterministic versus non-deterministic. Here, here you can see FMS can be broadly categorized into two main types, distinguished by how they are handling transition from given state and input. So deterministic FSM, they call DFSM. For every state and every output, there is exactly one defined next state. Another behavior is entirely predictable, non-deterministic. So this is the example for FMS, FSM. Non-deterministic for a given state and input, there can be multiple possible next state or even no next state. FMS FNFMS means offering more flexibility in modeling. So next we can discuss a classical example for finite state missions. Trustling F, the trustling FSM, a common illustrator of FSM principle is a behavior of a sampling transition, mapping across axes based on the inserting and pushing the arm. Uh, Locked in first stage, locked state. Uh, the initial state of preventing passage. Coin interested. Second stage, coin interested. Input. A coin is dropped into the slot. The next step, unlock the state. The trustling now premised passage. And the fourth step is push arm input. The arm is pushed by the person passing through passing through. The fifth step, back to the log. The trusting relogs waiting the next coin. Designing of an SFSM design designing of an FSM step by step. Create an FSM involves a structured approach from the conceptualization to implement the verification. First step, diagram or table. First step, diagram or table. Begins by sketching a state diagram or beginning with a sketching a state diagram or an outlining state transition table. And second step, state encoding. Assembling a binary codes to each state often using flip-flops in the digital circuits. And third step, logical definition. Define the logic for a state transition and many association outputs. And fourth step, implement the circuitry. Implement circuitry. Build the combinational logic and the state registers if hardware based means hardware based circuit you have to implement. And fifth step, verification. Test the FSM with a previous input sequence. The previous input sequence. The correct behavior. The correct the behavior. The next example, vending machine FSM. A vending machine is a perfect real world application for a finite state machines, meaning money input and product dissipating. Dissipating. Uh, this is the key features of a vending machine. State represent the accumulated money and the inputs are different coin denominations and a vend signal is triggered when the required amount is reached. Intelligent handling of overpayments and detaching the remainder for the future purchases. This FSM ensures accurate transitions and customer satisfaction in the automated system. Uh, Financial missions varieties, more versus medium missions. Here we see that while all systems manage manage states and transition. More and mean emissions differ in the how they are generated. Generate output influencing their design and the applications. First, more mission. Outputs are slowly determined by the current state. Outputs are slowly determined by the current state. They change only when the FMS enter a new state. The mean emission output depends on both current state and the current input. Current state and the current input. Output can changes during a transition, making them more reactive. Uh, Practical applications of finite state missions. Finite state missions are not just theoretical constructions. They are integral to many technological systems we encounter daily. Digital circuits, for example, digital circuits perform simple concepts in a complex controller in microphones, and software engineers crucial language for a pricing language, mapping network protocols, and defining software component behavior. Game development, detecting a character action, enemy AI, and state transition logic. Registering used in natural language processing and syntax language modeling. Everyday, we use day-to-day life devices. The logic behind the traffic lights, vending machines, and automatic doors. Why FMS matters? The power of simplicity. A finite state mission offers an intelligent solution for a designing and understanding the complex sequential sequential logic, interpreting much model and clear models provides a manageable and innovative models for a the critical sequential behavior and predictable design, conceptual foundations, and versatile tools. Here, a prudential design enable to create of systems that they predictable and reliable and easily testable. Conceptual foundation server as a foundational building block for a more advanced conceptual modeling, including turning machines. Versatile tool, an essential concept across computer science, engineering, and various other scientific disciplines. Explore FMS to matter system designs and computational fundamentals. Thank you.